Good morning, my dear kids. I'm Sridhar physics lecturer. So, in today's class, we are going to discuss the refraction at spherical surface in the ray optics. That one. So, I think it was a long journey for most of you. By this time, might have been using the app in my website. So, we have the app called as Physics Numericals in the Play Store, and also the website www.physicsnumericals.com. The logo is what we are having. So please do download the app and please do share to your friends who are badly in need of it. So let me start the class. So once again, students, welcome to the physics numericals. So in today's class in the ray optics, we are going to discuss the in the refraction at spherical surface. First, we'll start with the theory, then we'll explore the numericals. So let me begin the class. Now, as you have come across refraction at plane surface, now we'll go for refraction at spherical surfaces one. Let me assume a spherical boundary. So let this be the axis, what we can call. So let me keep an object here. Let this be the air, this medium, let it be air. Let the refractive index of this be mu1. Let this be the some denser medium whose refractive index, let it be mu2. What we have the formulas, no? Snell's law of refraction, the same thing is you are just applied for if the surface is spherical, then we are going to apply the Snell's law. Let the refractive index of this be mu2. Then I kept an object here. So then this particular thing will define this is the center of curvature of this. This will become the normal. This is the normal. So now let me choose the incident ray. The incident ray will be appearing here like this. So this is the incident ray. This is the object. A real object it is. I kept a real object in some air or let this be a glass. So this will be a rarer medium, no? And this will be a denser medium. Now I kept an object. This is the curved boundary here. There's a particular thing is a curved boundary. Now let I1 be the angle of incidence. Then we'll go for corresponding the angle of refraction. Now the refracted ray will undergo refraction. Let it meet somewhere the axis at this particular point. Let it be I. And this particular thing is the normal. So now what is this one? This one is a normal. Fine. Now this is the incident ray, this is the refracted ray. So now as the ray moves from rare to denser medium, the ray should bend towards normal. So the angle made by the refracted ray with the normal will become the angle of refraction. Let it be I2. We'll have this assumption first. Okay, now this the incident ray, the incident ray will make an angle with the optic axis. You can call this as axis or optic axis, whichever you prefer. The incident ray will make certain angle with the axis here. So let that angle be alpha. The refracted ray after refraction will meet the axis at point I. So where this will make an angle, let it be beta and let this be gamma. Okay, let me call this as point P. This is M. What we are trying to do is this is mu1. Let me use this space for all the distances I'll measure from the axis here from this particular point P. And what all I consider this incident rays as the refracted ray, they are the paraxial. Means only for paraxial rays we are discussing. For what we are discussing is for paraxial rays. So therefore, what we'll write is so here m will be very close to p because of this. M will be very close to the p. So what will happen to that angles alpha, beta, gamma? They'll be very small. We can do some approximations here. Now, what we are discussing is for paraxial rays. This is the one basic condition. For paraxial rays, m will be very close to the p. Now, let's apply the Snell's law. Apply applying Snell's law at m. Then mu1 sin I1 equal to mu2 sin I2. Then for paraxial rays, as due to paraxial rays, so we can do this approximation as mu1 I1 sin I1 will become I1, sin I2 will become I2. This is one equation, we'll write it. So now look at the triangle. From the triangle OMC, so what we can write, I1 equal to alpha plus gamma. From the triangle CMIMC, what we can write is like gamma equal to I2 plus beta. This triangle, look at here, triangle OMC. The sum of interior angles should be called exterior angle. This I1 is exterior angle, alpha and gamma will be interior angle. So therefore I1 I can write alpha plus gamma. This will be exterior angle. These two are interior angles. So gamma equal to I2 plus beta. So let's substitute these things. So here this is equation 2, equation 1. So put I1 equal to alpha plus gamma. So this will become mu1 alpha plus mu2 beta equal to mu2 minus mu1 into gamma. What are this? Alpha is very small. I can write this alpha as 10 alpha. Beta as tan beta. So mu2 minus mu1. Gamma as tan gamma. From the triangle, here look at it. As m is very close to the p, so we can just treat it this is alpha, beta, this is gamma. These distances will indicate here. This will be u, this will be r, and this will be v. Object distance. All the distance I'll measure from the axis, from the pole. What is p? P will call this as a pole. Just will give some name for it. Let this be pole. So all the distance I'll measure from the pole here. So object distance I'll measure here. And this is the radius of curvature of this surface. R is the radius of curvature. And the image distance is what? V. So here these quantities will be indicated here in this way. This is U. This is R. Substituting this, so from the triangle, what is the tan alpha? Pm by Tan alpha, you can write it as Pm by Po. Tan beta as Pm by Pi. Tan gamma as Pm by Pc. Then anything directed towards right, I'll take it positive. So how do I measure object distance from the pole? All the distances u, v, r are measured from the pole. There's one condition I'll put it. U, what is u? Object distance. What is v? Image distance. What is r? Radius of curvature. All the distance I'll measure from the pole here. So let me write one more step. So this will become PO mu2 minus mu1 by PC. What is PO? PO will become object distance. Minus U. Why minus U? Because I should measure object. This is a real object, we have kept it. Where the object? Object is in, say, some rare medium, and I'll measure the distance from here, no? So I'll measure distance opposite to the direction of incident ray. Any distances measured in the direction of incident ray should be taken as positive. This is the incident ray, no? And this is the incident ray. So the direction of incident ray is taken as positive. So therefore the PO will measure opposite to incident ray. So therefore this will be minus U. What about PI? PI will become plus V. PC will become plus R. These conventions are very important. So finally we'll land up with the formula like this. So what is mean by mu2, mu1? There's a formula what we derived. So to find out the location of where the image is formed, so we should use this formula. We know object distance, we know mu2, mu1, we know radius of curvature. Substitute, you'll get the image distance where that image will be formed here. So once, like if you look at the this one, so we should be aware of this particular formula. So if you look at this, what is mu2, mu1, mu2v? So what do you mean by mu2? This expression I'll rewrite in this way here. Refractivity Ri of medium in which refracted wave is present by, this is image distance. Then what do you mean by mu1? Refractive index of medium in which incident ray is present, and this is the as usual these things will be the interpretation of that formula. What do you mean by capital R? Radius of curvature of boundary. It's not that what do you mean by mu2? Where the refractiveness of medium, where image is present? No. The refractiveness of medium where the refracted ray is present. The image can be in the denser or rare medium. This is the something very, very, very important. This particular, I'll just indicate what we were. What do you mean by mu two? Mu two means this one. Irrespective of image, image and object can be both be in rare medium, both can be denser medium. This is mu one. Mu one is related to this one. I think this is something very, very essential part of the discussion what we are making it. What is this formula? This formula is used to find out the location of image. If you keep object in some medium, the ray after the incident ray will undergo refraction. After refraction, the refracted ray will meet the axis at some point. How to calculate the location of that image, where that image is formed? That particular position of image can be determined using this particular formula. And what we did, we just applied the Snell's law. Who was helping us? The Snell's law was what we studied, the Snell's law for plane surface. Now that is being applied for spherical surface. Okay, now you can ask few questions. So where we have kept object? Object is in error medium. We assumed it, and it is facing some sort of convex surface, no? And the image is formed. That's what our derivation is. What we did. Is it the discussion? This formula is it applicable in all the situations, or only for this particular condition? Means now the our primary concern is like, is it this a generalized formula or is it applicable only in few specific cases here? No, it is applicable in almost all the situations, irrespective of whether object is in rare medium, in denser medium, image formed in denser medium or rare medium, object facing the convex surface or concave surface, it's applicable. Means the same formula is readily applicable in almost all the situations. Hmm? So we will generalize it now. Let me construct one. Okay, we'll use this one. Now I brought a situation. The first one, just now what we discussed, no? Now, if object is here, object, what is the condition? Object is placed in rare medium facing the convex surface. Look at the boundary. The boundary is a convex towards the rare medium. Let's assume that this is a rarer, this is a denser. So the incident ray, this is a boundary. Boundary will, so look at this normal will indicate here. Already just now I discussed that I'm summarizing it. So we will get the, this is the thing. It can, and this is the image. Okay, this is the incident ray. Now it can happen a situation where object kept in rare medium, the image is formed in denser medium. That's what you're seeing. Now I can bring a situation where still it is a denser. The ray will undergo refraction and it will bend slightly. Now the ray, it will bend slightly. It will not bend more, it will bend slightly. Get that one? So where the image, I think I'll bring it here. We'll extend this line backward. So look at the image formed. So here is what? The image. Hope everyone is getting this is center of curvature, this is P, this is M. What we had the discussion, no, it can happen. So still that formula is very much applicable. Look at the image. Earlier the image was in denser medium. Now where the image is in again that medium. Object and image can be in both in same medium. Instead of bending more, the ray will bend slightly. It all depends on the value of mu2, mu1, and also the object distance. Now we will have a situation where let me select this part. Yeah. Now I'll keep object in denser medium. Let this be the object, and this is the radius of curvature. Normal, this would be normal. Now the ray will be incident. Now the ray is moving from denser to rarer. So it will bend away from normal. So after refraction, the ray will meet here. So now where is the object? Object is in denser medium and the image is in rarer medium. That pink color dotted line is the center of color. This is normal. Okay, this is the thing. So now I'll bring another situation here. Now the ray is moving from rare to denser. It will bend slightly. It should bend away from normal. It should bend away from normal. Okay, then. Slight correction. I'll make it. This is one more situation. We may end up like this. Now the ray is moving from rare to denser to rarer. So it should bend away from normal. It should bend away from normal means it can happen like this. This image. So this is the incident ray. This is a refracted ray. Look at now where the object is in denser medium and the image is in the same denser medium. So sir, can you say anything about nature? This is a real object and we are getting the real image. This is the real object. We are getting the virtual image. Here for real object, I am getting the real image. Here the real object, but the image is virtual. First case, the object was kept in rare medium and it was facing the boundary such that the boundary was convex towards the rare medium. Here, the same condition. The object was kept in rare medium and the boundary was facing the convex part of the boundary was facing the rare medium. Here, object is kept in the denser medium And the boundary what will happen here is facing the rare medium, but look at this one here. Now it will be concave towards the object here. No? Object can be in rarer medium or in denser medium. That's what I mean to say. In all these cases, still that same formula what we derived is applicable. One more, I think one more case is there. I'll introduce that. Geometrical shape, little bit difficult to construct. Yeah, I'll some rough diagram I need. Okay, now you see this. I'm going to keep the object in. I'll keep the object in denser medium. Where the center of curvature of this will be here. This is the center of curvature. Now the incident ray moves from rarer to denser. So what should happen to the ray? Should bend towards normal. The ray should bend towards normal. Okay, this is the image. This is a rarer medium. This is a denser medium. So there's a real object and there's a virtual image. That is formed. Okay, there's a one situation. Next situation, the object is the center of curvature, let be here. The object is kept here, we're in denser medium. So there's an incident ray. Now the ray is moving from denser to rarer. Should bend away from normal. So away from normal will be of like this. So if you produce it back, will come like this. So this is the image. Rarer, denser, this is a real object, virtual image. Okay, now in all the cases, is this formula applicable? Is the formula what we had, what we derived in the previous section, is very much readily applicable. Just you have to use that formula here. So now mu2 v minus u equal to mu2 minus mu1 by r. This is the formula which is applicable in for all these situations. There is no any limitations of this particular formula that it is applicable here, it is not applicable here. Means object is in rare medium, image formed, and object is facing the convex boundary, and the image is formed in denser medium. Is this formula applicable? Yes. Object is in rare medium, and the object is facing the convex surface, and the image is formed in the same rarer medium, not denser medium. There's a difference. So is this particular something happened. I'll get it back. Yeah, okay. Now look at this one. Object is in rare medium. It is facing the convex boundary, and the image will be formed in the rare medium. Is this formula applicable? Yes, it is. Now what is the next situation? Object is in denser medium. It is facing the concave boundary. You can see this concave boundary, and the image will be formed in rare medium. The same situation here. Object is in denser medium. It is facing the concave boundary, and the image is formed and the image is formed in the same medium, that one. Still this formula is applicable. Now what about object? Object is facing the concave boundary, is kept in rare medium and is facing the concave boundary, and the image is formed in the same rare medium. Similar situation here also. Object is in denser medium, image is formed in the same denser medium. So and you can see this, still this particular formula is applicable. I think you do get conditions like this. So if this formula is applicable, it's very much. Next, what is V? V is this image distance you should measure from here, from P. This is V. This is U. What about here? What about U here? U is this one. This is U. What about V? V is measured from P. In all the cases, all the distances are measured from P. So in the formula, what you should do? All the distances are measured from the pole, and this is the axis. The direction of incident ray should be taken as positive, and you have to substitute all these things with sign. The use of this formula is all about refraction at spherical surface and the lens. What all we do, problems, refraction at spherical surface and the lens, is what this particular primary formula. I think I just giving some description. Maybe as when we get into numericals, no, you'll be in a far better position in you how to use this particular formula. Just I wanted to show you, irrespective of whether object kept in rarer or denser medium, object facing in convex surface or concave surface, this formula is applicable. What is mu 2? Mu 2 is not something like where refractiveness of medium this refractiveness of medium where uh, it will be like this. Refractiveness medium where image is present. No, where the refracted ray is present, that is mu 2. Similarly, in this diagram, sir, can you indicate mu 2, mu 1? Yes, will indicate. What is there in this diagram? This will be mu 1. This will be mu 2. Mu 1. This will be mu 2. Mu 1. Mu 2. Mu 1. This mu 2. Okay, after this, we'll go for the magnification formula. Just make observation of these things. Linear magnification. We'll derive the formula for linear magnification. Let me go for a boundary, spherical boundary. Let this be the axis. We define it. So let's go for, let me keep in some extended object because I have to define the magnification. No? Let's take the some extended object. Before that, this will be the point P. This will be the center of curvature. I'll keep an object here in this way. Okay, let this be the object O AB. So we'll at this extended object it will send many rays. So we'll assume one ray. We'll assume one ray, which is passing through the center of curvature. This is like some sort of normal, and any ray passing through the normal should go undeflected. Any ray which is passing through the normal should go undeflected. Then, okay, let's take the incident ray. This is the incident ray. Then this will be the refracted ray. Now this is the image position. So this is the object, this is the image. So let this be the mu2, let this be mu1. So this is HI, you write it. What we have to just get expression for magnification. So then what are other things? Here this will be radius of curvature. This will be the image distance. This will be the object distance. Then uh, let this be the angle of incidence, I1. Angle of refraction, I2. What is I2? I2 is angle of refraction. I1 is angle of incidence. Let's get into applying Snell's law. Mu1 sine I1 equal to mu2 sine I2. As we are discussing for paraxial rays, so sine I1 will become tan I1, tan I2. So what is tan I1? Tan I1 will be AB by PA. Tan I2 will be A dash by PB dash. PA dash. Now further, AB will become height of the object plus HO. Anything directed towards upward is positive. Anything directed towards right is positive. Direction of incident ray is taken as positive here. What is PA? PA will become minus U. Mu2. A dash B dash will become HI. So PA dash will become plus V. So finally, how you define magnification? Let's simplify this. Mu1 by mu2 B by U equal to HI by HO. So what is the basically magnification formula? Linear magnification, small m. Height of the image, what is HI? Height of the image. What is HO? What is small m? Small m is linear magnification. So what we know, on one side we know this formula. What is the use of this formula? We can locate the position of the image. Using this magnification, we can predict the nature and the height of the image. I'll just summarize. So using this, it will, we can find position of image. Using this formula, we can find nature of image. I think this is what we needed, no? Whenever you keep object at spherical boundary, and this is the spherical boundary. Oh, by everyone is well aware. So whenever if a object is kept nearby a spherical boundary, can we find out the location of that image formed due to refraction of the rays? Yes. Can we predict the nature of image? Yes, it is. This is the one very fundamental formula is what we have obtained now. So what is all our next numerical discussion is how to use this particular formula. Next question comes. Is it confined only for spherical boundary? What happens if the plane boundary comes? Can we apply S for plane boundary? R will become infinite. For a plane boundary, the R will become infinite. So this formula is applicable both for spherical as well as plane boundaries or plane interface. Applicable for both spherical and plane boundary. For plane boundary, R will become infinite. We can easily tell the position of image and height of the image, all the quantities, what all we studied, refraction, plane surface, all those things we can apply back here. Okay, kids, like this is the way of like a refractionate spherical surface. What we derived is we derived an expression for like if you keep an object nearby a spherical boundary, then how to calculate the position of image and also the nature of it. Position of image is given by this particular formula, and the nature of image is position of object is given by this particular formula. Nature of image we can predict with the help of this particular formula. Okay. Okay, kids, like in today's class, we had the discussion on the refraction at spherical surface formula, where we derived the formula for to locate the position of image if an object is kept nearby the spherical boundary, how to calculate the position of image, and also how to predict the nature of image, or if an extended object is kept, how to calculate the height of the image. These are things what we derived it. Okay, just once again, if you could not understand, watch the video again, think on it, understand it. In coming class, in tomorrow's class, we will focus on the how to use this in various applications. Tomorrow we'll focus on the numericals. So thank you all of you. Thank you very much. Please do share the app and share the web information to most of your friends who might need this particular app and all those things. Okay, bye kids. Take care.